afternoon, everybody. Hope you are not in food comatose yet, and we will make it over this food bump together. Preface with a disclaimer. This is not going to be your typical Houdini presentation. This will be a bit more research-focused, presenting on what goes into tools that we might be able to pull out to the community, to push out to the community in the future. And honestly, until yesterday, it wasn't entirely clear if I'd had something to present at all, which I have now. So I'm going to show that today, so let's dive in. Title of this is Prompting ISO 2023, Researching New Interfaces for AI, or what might or might not make it into future MLOps versions. In the machine learning talk yesterday, who did that? You're here? No? Yeah, you're here. Perfect. You might have realized that ML is often about dataset creation, curation, and efficient compression. And this one is about dataset exploration. Or more precisely, about a neural network's world model and what it learned. Yes, this talk is on AI, and you think, yeah. But also, this one is about creativity, which is nice. But still, my disclaimer, we are middle-aged white folks. What worked for us might just be dumb luck. What I'm saying might be stupid. I'm very happy to discuss this in the Q&A, and researching is hard. So before we dive into this, here's a motivation, different types of creativity. And this is after Margaret Bowden, who's one of the more prolific research into human and machine creativity. So in her opinion, there are three major types of creativity. Combinatorial creativity, that means unfamiliar combinations of familiar ideas. To give you an example, this is Kurt Schwitter's The Unimage, a collage early 20th century. So taking pre-existing stuff, rearranging it into something. Then there's transformational creativity, transforming a conceptual space. An example for this could be pointillism, Paul Signac with his breakfast here, where you're taking pre-existing concept, just taking it somewhere new, stylistically, exploration-wise. And there's exploratory creativity, that means exploring conceptual spaces, and this is where we'll mostly be dabbling today. So in this example, and this is an old one, I generated abstract space sculptures from stable diffusion. So that is exploring the spaces that these neural networks have learned. And my motivation for this is my firm belief that prompts are the worst. Because think about it, how would you explain what a Picasso is before a Picasso even existed? And in my opinion, at this point, we are with AI models, is that it's a totally new medium which tries to emulate old media. And we were better off exploring this as a totally new medium than trying to emulate what's been before. And human language, at this stage, currently isn't the best way to do that. So what are my goals? To just give you a few image ideas. I want to generate images like these. Not necessarily images that are commercially viable immediately, but have an artistic value and are hard to describe with human language or hard to pinpoint with single sentences or single individual prompts. You would have to write whole sentences to maybe describe the visual worlds behind these images, or these, stuff like this, or maybe these, although these are the most concrete of the bunch. Before we get into how we're doing that, let's get everyone on the same page of how the whole thing actually works. Please raise your hand who's already seen this, maybe in another presentation of myself. So this is about the data sets that go into AI and how AI generates images. Who's already seen that? Who's not seen it? Okay, good. Good. Okay, base data. The base data we're working with is extremely biased, and my claim here is that men are ugly and the data proves it. So we'll be looking at a data set called Lion 5B. That's the base data set for the original stable diffusion. 5 billion images scraped from the internet, annotated by humans and also by machines. And not only annotated with tags, what's in the images, but also with an aesthetic score between 1 and I think 9. Either it's 1 to 10 or 0 to 9, something in between there. So let's look at the dataset, and there's Dataset Explorers where you can search through the dataset, and let's search for women. Women with an aesthetic rating, it's hard to see here, but it's at an aesthetic rating of I think 1 or 0, which usually turns up these placeholder images from image databases, because that has nothing to do with the concept we're searching for. It's not aesthetically pleasing in regards to that concept. So the worrying thing already starts when we increase this aesthetic score to 3. This is 3 out of 9 aesthetic score for women. This is what you see in advertising models. Very symmetrical, very Caucasian, very young, very slender, very athletic, very unrealistic. And the really, really troubling thing happens when you prompt for women with an aesthetic rating of 9, where you get to these doll-like images who get frighteningly young at some point. Meanwhile, to drive home my point, let's look at men. Again, start with men with a low aesthetic rating, and you get your standard placeholder images. Nothing unexpected here. Let's increase the aesthetic score for men to 3. And you get, again, primarily Caucasian dudes, slender, not above 45, I'd say, and mostly in business attire. Okay, let's increase the aesthetic rating to 7, and you get your hipster dudes, you get your occasional beards, and your occasional t-shirts, but still, symmetrical, slender, young. Let's look at men with the highest aesthetic rating. My theory for this is following, and I have no data to prove this, but my theory is that the data has been tagged by humans and mainly by heterosexual males. And in my opinion, or in my life experience, heterosexual males have issues with admitting they find an image of another male highly attractive. So the ones remaining that are rated high are abstract concepts like gingerbread men or teddy bears. So just when we're talking about this, the data is massively flawed. So let's look at the mechanisms that have been trained using that data and how we use them to infer, to generate images. And this is your standard, what's called probabilistic denoising diffusion model. It's the building block for stable diffusion and nowadays also for FLUX, a new version of this. So we start off with a prompt, and we are prompting for a parrot wearing a tuxedo. The first thing is this thing gets tokenized. That means broken down into a list of integer numbers. Every single word or part of a word, if we cannot find that word in a dictionary, gets a concrete number. And that is literally the numbers that this will turn out. And these then get piped into a first neural network, a text encoder. And this, out of these individual tokens, will generate a list of numbers. In most cases, a list between 1,000 to 2 million numbers. And we call this a text embedding. And this is already what's living in what we call latent space. More about this later. For now, you can think of this as a direction in space. Also, when generating an image, we need to start somewhere. We start from noise and feed this into an algorithm that is stepwise trying to remove the noise from that image, meanwhile trying to maintain that direction and try to denoise that image into what is a parrot wearing a tuxedo. And we do that stepwise, always removing a tiny bit of noise, going towards a parrot with a tuxedo, etc., etc., etc. And if we do that often enough, we end at this, our parrot wearing a tuxedo. So the question that I ask myself is, how do we actually art direct this in novel ways, other than prompting? And let's start with a very old idea that's been there since embeddings and latent spaces have been researched, that is semantic arithmetics. So now that you have directions for concepts such as man, women, or king and queen, why not do math with it? And why not subtract from king, man, and add woman to it? Should give us a queen, right? So let's try. This is the vector for king visualized. This is the one for man visualized. This one for woman. And if we do the arithmetic, king minus man plus woman, we arrive at this. So when you compare it, you've turned your king arguably into a queen. That is kind of mind-blowing when you've grown up in a time where computer science was at the stage where I graduated. But now it's kind of boring because people doing it over and over. So what could we do with this? Well, let's try something like this. And I feared for the worst when entering this. I expected the worst and was pleasantly surprised when I arrived at these spaces here. These haunting, between realism and abstract painting, photography worlds that we get there. And I want to arrive at these spaces more reproducibly and more easily than just trying random sentence arithmetic. So how do we art direct this now properly, now really? Well, let's have a look at the latent spaces. I've been talking and mentioning about that. So how can you imagine this? Think of it as a map of the world that a model learned. And on this map, you can plot every concept that there is in human language. For example, down here we might have an island of parrots. And if we take one of these points and turn it into an image, this might be the image that we arrive at. Up here, we have the same, an island of tuxedos. Next to this peninsula, which has this weird thing. Any ideas why this is coming up? Just shout at me. Penguin? Penguin suit. One theory, my theory is this is tux, the Linux symbol. So I think it's close to tuxedo for that reason, but might be penguin suit as well, yeah. And what we do, theoretically, when deriving an image is, with the noise, we just pick a random point on that landscape, on that map, and then using an embedding, in this case, the parrot wearing a tuxedo, giving us a direction in which we step-by-step march, step-by-step denoise that image, to arrive at our parrot wearing a tuxedo. This has been in 2 dimensions. Now you just add your 700,000, 2 million vectors, and you think of it at the same point. That's your latent space. And what you can do with this is actually visualize the prompts you do. This is prompt interpolating between a parrot, a tuxedo, and a parrot wearing a tuxedo. And you can really see this horseshoe way around, so we're arriving at the same point in the latent space. So we're doing full circle. Or here, this is a detail of me blending between the prompt for a pizza and a parrot. And if you zoom out a bit more, you can see the pizzas are nicely clustered down there with the parrots up there. So that space is semantically ordered. Just to drive it home, another example is digits here. Chris Kopik did that. So he mapped an MNIST data set, very popular data sets for digits, into 3-dimensional space. And you can see the clusters here. The 7s are all in the upper corner, the 6s and zeros down in the lower. And depending where in 3-dimensional space you are, you get different digits or different images of digits and anywhere in between out of this. So a clever way of not only compressing your data, but also arranging it in a meaningful way. So, where do they come in? I mentioned this. We are driving the denoising process using those, just informing it into which direction to go. So what can we do with it? For example, let's take a point on the map. For example, in this case, generating a parrot image, and then just scatter random points around it. Just do a drunken men's or drunken person's walk around it and see what images come out of it. And the further we get away from this original parrot here, you can see at first we're still keeping that concept of a parrot with sometimes really beautiful images. But the further we get away from this, the more we are diving just into the concept of parrot-ish shapes with sometimes really weird examples. And the further you get away with it, you just at some point arrive just at parrot-shaped or parrot-inspired noise. You think, yeah, that's nice, but we already had that a year ago. And how about a bit more of a comprehensive map, or atlas as we call it, of these embeddings? Because in here I showed you like a map of maybe 100, 200 embeddings, and that's definitely doable on your and my machine. But how about something bigger? Well, it turns out that is computationally not as easy as I wished, so I put it on the back burner. And then this happened. I got contacted by these lovely folks with these lovely letters. That's the Barcelona Supercomputing Center. More specifically, the DataVis team. And I've been working with these 3 fine people who originally used Houdini to do science visualization and science communication, mainly for climate modeling, for biomedical, for shockwave research. And you might know these folks and these institutions from popular culture because this very computer called Mare Nostrum 4 has made it into a Dan Brown novel. I think some weird quantum black hole has been discovered there in the novel, and is really nicely situated in this former chapel. However, that's currently been torn down and rebuilt as a quantum computer, and they have this instead, which is Mare Nostrum 5, apparently one of the 10 most powerful computers in this world. So suddenly the questions changed. Can we build a comprehensive atlas in FLUX, which is the new model, which is a bit more, not only a bit more, but which is massively more capable than Stable Diffusion. Blows most of the other models that are out there, including Midjourney, out of the water. So what we want to do is build a map of all these embeddings that these models have into a 3-dimensional map, and then hopefully from this map, pick a point and be able to generate an image out of this. So basically what we're going to do is prompting, embedding, 3D coordinate. And the technique we're using is called UMAP. That's a typical, what's called dimensionality reduction algorithm. An analogy would be you want a 2D image of a bush or of a tree. And you have a wall behind the tree, and you take a spotlight and shine it on the tree and observe the shadow that's forming on the wall. You could think of dimensionality reduction in this case. It does a few more clever tricks, but let's not occupy ourselves with that for now. So, for Stable Diffusion, the embeddings have this shape. So it's a list of 77 times 768 numbers. And that's drawn to scale here. So this is your Stable Diffusion embeddings. Turns out FLUX has a bit larger embeddings, comprised of what's called T5 embeddings, which is the orange part, 2 million components. And there's a tiny sliver of blue down here, which is the clip part, those 768 components. This results in massive computation times when you want to do dimensionality reduction on this. So this is a bit our chat. So this is, I think this is Sunday or Monday. Kenai has point cloud. Nope, longer than expected. And we're talking rendering or working on this computer here. So this is Monday night. And at this point, IT shut us down because we're crossing the petabyte threshold on the machine. And that's where they say, okay, now cancer research has priority over your shit. So let's panic and reread the paper. Turns out in the FLUX paper, and literally this happened Monday to Tuesday night, I just was panicking and reread the paper, stumbled upon this paragraph, and it says here, for most prompts, however, we find that removing T5 at inference time still achieves competitive performance. Because what this means is, screw all the orange part. You can throw that away. Put zeros in there. Just take that thin sliver of the blue here, and you will be able to achieve a comparable performance. So let's try that out. Here I prompted for a cat holding a balloon, and you can see this is the one with large embeddings, and this is the one with small embeddings. While visually different, the concept still holds, and that's what's important in this case. So now we are able to take a dictionary of 250,000 English words, standard dictionary, and turn it into an atlas that looks like this. So this is your embedding space of FLUX, and imported in Houdini. And once you're working for a few weeks in Python, you realize how fucking performant Houdini is over Python in visualizing and working with those. So that's the embedding space here in 3D. And here I'll show you just randomly, and literally randomly zoomed into this cluster. And this turns out to be the weed cluster. So not only do you have weeds in here, but also all sorts of cannabis-related words in here. It clusters. Again, it clusters by meaning. Or if you zoom out here, I'm not sure what I think I'm going to something with the books cluster with bibliographies and stuff. Yeah. Or here, when you're looking for a dog and zoom out a bit, the first thing you see is other dog breeds, just like a corgi or a dachshund or a schnauzer. And the further you zoom out, you see other animals clustered around this. And this, I think this is the snake cluster or whales. Yeah, here's the snakes and here's the rabbits, I think. So the clustering works. Now we need one more step. We have this atlas. How do we generate an image out of that? How do we reverse that? So basically, we're just taking now a shadow and trying to make a tree out of that. Luckily, UMAP comes with a technique that's called UMAP inversion that allows us to calculate back from a 2- or 3-dimensional point in space to an embedding, and then from that generate an image. So to test that, what I did is I took an embedding and piped it straight into FLUX, in this case, still stable diffusion for testing, and then UMAP this to a 3-dimensional space, picked the very same point that generated this image, turned it back into an embedding, and calculated the resulting image. And that, my friends, is not too convincing. And it turns out that inversing UMAP is really hard. So let's be stupid. Let's just take the nearest points and from them interpolate the original embeddings. And let's try that. That gets us closer. And all the while is faster. And admittedly, while not being perfect, the error in the embeddings is way smaller. And it wants to turn this dude into a dog, but at least the pose and the framing kind of matches at this point. All right, again, this is all stable diffusion. By this point, a toy data set. By toy data set, I mean it's just like, I think it occupies 2, 3, 4 gigabytes of RAM on your GPU currently. So let's test that in FLUX. Are there any surprises? Again, same strategy. Original image, turn it into latents. 2D, 2D back to latents, back to image. And yeah, while not the same image conceptually, it holds. This one as well. And you've got your hits and misses, but I'd say nice-ish enough. Thing is, FLUX is big. FLUX, in its original state, won't fit on your 4090 GPU, so 24 gigabytes of VRAM might not be enough. So let's try what's a quantized model. That's the models that have been pushed out, that are more efficient, that will fit into your high-end graphics card, but they will fit on a single computer in a tool that you can realistically buy. So again, original latent, turn it back to 2D, back to latent, back to image. Let's try that again. And again. And if you're thinking anything like me at this point, you're thinking, because even when you take the difference of these images, there is no difference. They are exactly the same image. So at this point, I'm starting to freak out because this is an error. Because the thing that I regenerate from the 2- or 3-dimensional point is not exactly the same thing. That should not result in the exact same image. So what the hell is going on? What is quantization, actually? Let's look at this. So when you want to load a normal model, what it typically does, it will overflow your GPU's VRAM. It won't fit in there. So how can we get the memory footprint of that model smaller? Well, let's ask ourselves, how precise do we actually need to be? How precise do we want numbers in this model to be represented? How finely granulated do we want those vectors pointing in some direction? Give you an example. Let's take a number between 0 and 1. And let's take a fine-grained version of this. In this case, a number here can fall into 32 buckets. So I'd have to provide for 32 buckets, which is that 4 bytes, 4 bits, 3 bits, 4 bits, 5 bits. You'd have to provide a certain number of bytes. This one here just has 4 buckets. Lower byte count, lower bit count. That means your model will fit better into your RAM. However, what happens now is with any number here, any arbitrary number, let's pick this one, and I want to save this. In the top data type, I can do that. It's exactly this number. In the lower data type, I land here, and I have to decide where I want to put this. And realistically, what I'll do is I'll put this in this bucket and save it as a 0. So basically what happened is my previous 0.0625 number is now a 0. Anything that falls into this range will be saved as a 0. So that, on the other hand, means that the error I have in my original vector pointing somewhere just doesn't matter at this point because it's pointing at the same damn bucket. So this actually is nice. So, now that we're there, what now? Currently, we are running this and generating images from the embeddings in order to be able to have the users have something visualized with the point clouds. And we are not there yet, it's still running on our computers, but I wanted to give you just a sliver, a look into what this model does. And FLUX, although very good in image quality, has its biases. For example, it often wants to generate these types of images, the red-caped superhero or supervillain. That's what comes up surprisingly often, just by prompting English language. And some of them are literally like what or where, and it does that. This one is another very popular motive that it does, the cutesy kind of 3D-ish toy figure. And then, of course, and I'm not sure if anyone of you is triggered by mild sexuality or sexism, but that's just a trigger warning for the next slide. You have your preconceived notion of what male or female bodies look like. Again, not necessarily a very realistic presentation of the world. So, now we have that. What's next to do? Well, more comprehensive data sets. So what we want to do is not only offer you a glimpse into a 250,000 data points, but maybe 1 million, 2 million. Let's see when it starts breaking. That's the next goal. And at this point, just briefly, let me talk about a few tools that have been really, really valuable in research. So of course, it helps having a supercompute facility, but it's not necessary, especially once you start reading your papers properly. So with our new approach, actually I can run this on this and you wouldn't even need this. And this is just me just slamming in GPUs into a mining rig. Actually, this by now runs well on a single GPU node. Just for anyone trying to build their own cheap computational cluster, this is a decent approach, a mining rig. It keeps the GPUs decently cool, it runs a Windows or Linux, and you can control it by this thing, extremely valuable. PyKVM, it's an open source Raspberry Pi thing. You plop in HDMI, a network, and you can just remote control your PC. It even comes with a plug-in board that allows you to switch it on and off the PC. Perfect. But realistically, and there's the hippie in me, it's not about your tools, it's about the people you work with. So good collaborators. And where does this leave us? So, infamous last words, the learnings. Check your data. For example, in the beginning, when we were figuring out which words to prompt, we were looking at several different kinds of word collections or corpus. I think I'm not sure what the plural of corpus is. I would say corpi. The brown corpus, for example, we fed it in and let it run. And once you look at the corpus, you see it's not individual words, it's articles. So you have multiple words repeating, and just blowing up your data. And also read your papers multiple times, so maybe next time you discover that you can make do with a really small sliver of your data and not the whole thing. And then I want to drive this home. AI, in my opinion, is a new medium. Let's use it as such and not try imitating old media. Let's try getting art and artwork out of it that is worth it, that is unique, and that is only achievable using AI or neural networks. Also, research is hard and frustrating, but also research is very rewarding once you find out and you discover. And finally, research is incredible fun, especially when you have good-minded people. So, next step, we're remapping bigger atlases, bigger maps, generating larger image data sets, building a UI for this, hopefully finding a way to match up the points with the image data that does not bog down your typical PC, and hopefully get this built into MLOps. Looking at you, Paul. And one last thing, If you truly want to dive deep into those topics and might want to get a master's degree along the way, we are starting a new master's program at Nuremberg Tech, where I teach as a professor. So apply, designfordigitalfutures.de. Thank you.